Okay, so today we will start characterizing how meaning looks like. And for that, we will use something that you know. So in one dimension, so if you have a function that takes a real argument and uses a real number, and then you want to know if a given point is a minimum, then there are two conditions that you know these minimums has to fulfill. And these two conditions are if the function is continuous and differentiable. So the first one is that the first derivative has to be zero. And the second one is that the second derivative is positive. This would characterize the minimum. So if this is the function, at this point the derivative is zero. But if we look at some other interesting points, for instance, in a different place, the function does like this. Here the derivative is also zero, and here the derivative is also zero. So having a derivative that is zero is a necessary condition, but it is not sufficient. So it is not sufficient. If the derivative is zero, still you don't know if it is a minimum or not. So if you want to know if it is a real minimum, then the second derivative has to be positive. But here, the second derivative of this function, we are not plotting the second derivative, but the second derivative of that function is positive. And here it is negative, and here it is zero. So this is the way to distinguish different points of a function. So the points fulfilling these two conditions are minimum or minimum. The points fulfilling these two conditions are maximum. And the points fulfilling these two conditions are inflection points. Okay, so these you already knew. And now let's extend that to more dimensions. And before doing that, let's see how to use this knowledge. Okay, so let's say you remember the tank problem that we had yesterday. So we designed a tank that had minimum area, but it still contained some given volume. So this was the problem formulation solution. So this is the load function that is just the area of the tank. And then subject to this equality constraint that tells us that the volume of the tank has to be some given value, and the positivity constraints, because it doesn't make sense. Maybe I heights that are explorers. So so then one possibility, this is a function in two variables. So in two variables, the radius and the height. But then we can use the constraint to turn this variable, this function that depends on two variables, the function that depends on only one variable, that is the one that we already know how to handle through these conditions. Okay, so we use the constraint for that. This is the constraint. If we solve for the height function of the radius, and then you substitute the height here in the whole function. This is what you have. And now the area only depends on the radius. So you have gone from a function that depends on radius and height to a function that depends only on the radius by exploiting the constraint. And now we have a function in single variables. We can apply the two conditions that we have here. So if something is a minimum, it has the derivative has to be zero. And then we will start in the second derivative. Okay, so the derivative of that function with respect to r is this one. Now we set it to zero. So we set this to zero. And then you solve for r and add this. So absolutely. Okay, so now we know what is the radius. And if you know what is the radius, you know what is the height, because the height was through the constraint, activating the constraint. So simply substitute, and now you know it's the radius and what is the. Okay, good. But then we still don't know if that is a minimum or not. So we have to study the second derivative. So the second derivative of this function is this one. Okay, so it is the first derivative of this function. It's the derivative of the derivative. So it's one, the derivative of this one. And now it has to be larger than zero to be a minimum. So let's see. This is larger than zero, and this for any positive r, this is also larger than zero. So the whole thing is larger than zero. So that means that this point is a minimum. So yeah. So in this very simple example, we have seen that the first derivative equals zero is a necessary condition. If something is a minimum, it has to fulfill this statement. But then we have to check whether the second derivative is also is larger than zero to be sure that it is. And we have the solution. And in this particular case, the function is convex. And because the function is convex, and this is a minimum. So if this is a minimum, this has to be the global minimum. There is no anything better than that because the function is convex. Okay. And here we have a representation of that function. So this is the surface area as a function of the radius. And this is the function that we said. And then this is the minimum value that we have. Just calculate for a particular volume that I have said. Okay, good. So this is easy. This is something that you have for me can be. Now let's extend that to multiple dimensions. So let's say that now we have a function that takes a vector as an argument, produces a scalar value. And let's say that f is differentiable. Then a point can be a minimum, and it is as in the one-dimensional function. The first or the necessary condition is that the derivative is zero. The derivative for a vector valued function is the gradient. But the gradient has to be zero. The gradient, here you have the definition of the gradient. Where it is the derivative, it's a vector, but it's the derivative of the function with respect to all the variables. You knew the gradient before, right? So then, so the first order necessary condition, it is first order because you have only the first derivative. So first order necessary condition is this one, but this has the same, not problem, but same problem is as in here. So just having the derivative equal to zero is not enough. You need the second derivative to be larger than zero, to be a minimum. Okay, so what is the second derivative in a vector valued function? So the vector valued function, the equivalent of the second derivative is the Hessian. So the Hessian is defined in this way. So here you have the two notations for the Hessian. So the Hessian is a matrix, and this matrix is second derivative of f x1, second derivative of f respect to x1 and x2, x1 and xn, then x2 and x1, x2 square and so on. Okay, so, and this is one way to note it, and the other way to note it is with this nabla operator, with nabla square, that is the Hessian. But this thing and this thing is the same. So the condition is that in one dimension was second derivative larger than zero. So here will be this matrix, it has to be positive definite, that is the equivalent. And positive definite means all the eigenvalues are strictly larger than zero. So if all the eigenvalues are strictly larger than zero, then X star is a strict local distribution. Okay. Good. Very good. So then, let's try to solve the same problem that we had. But now with this new tool that we have for multivariate, so for vector valued functions. Okay, so we have this problem to solve that have two dimensions, two variables, and we have this constraint. This constraint is an inequality constraint. So we will construct something that is called the Lagrangian of this problem. Have you seen the Lagrangian before? Yeah. Okay. So then we construct the Lagrangian of this. So this is the function minus lambda, the constraint, this part of the constraint. And then we compute, so what was the first condition? The first condition was the gradient equals 0. And now the Lagrangian depends on three variables. So it depends on the two variables of n. And now it also depends on the lambda parameter. So that is the one of the Lagrangian. So now this depends on three parameters. So we compute the derivative with respect to the three variables. This derivative with respect to y of this three, derivative of with respect to h of the same, and derivative with respect to lambda. Actually, the derivative with respect to lambda is just a constraint. So we see that when we in the next step, when we say this has to be 0, this is just a constraint. Okay, so the derivative with respect to lambda is the constraint. Okay, very good. So then we set it to 0. So each one of the derivatives has to be 0. This is an equation system. It's a non-linear equation system because we have products like R8, R squared. So R squared 8. So it is a non-linear equation system. You cannot use matrices to solve this part. But still, you know how to solve the equation system. So we take equation 2, and from equation 2, you solve for lambda. Here, you solve for lambda. So now we can eliminate lambda from the equation. So we substitute lambda into the equation 1, because we have lambda here. Substitute. This has to be 0. So now it depends on the R and H. Then we can have a relationship between R and H. And now we go to equation 3, that is the constraint, and we substitute H substitute H, and then we can solve for that. It is the same solution that we had before. So a cubic root of 3 divided by 5. Say one that we have here. And now because we know the relationship between H and R, we can substitute there and we know H. Okay, so this is reassuring that we are getting the same solution as we had before, but now we have used the different technique. So before, what we did was turn this mode function into from 2 dimensions to 1 dimension, and then solving the problem in 1 dimension. But now we have fully solved in 2 dimensions, and so we have it extended 3 dimensions by including that. Okay, very good. Now we have the same solution. So in general, and we haven't checked here that the Hessian is positive. It is much more positive technique, but because it is much more complicated, but you get the idea. Okay, good. So then let's formulate the general problem. So the general problem is you want to minimize some function subject to some equality constraints. Then the Lagrangian is a function minus the sum of all these equality constraints. This part of the equality constraints times a lambda for each one of them. And if you compute what is this first order necessary condition, they are also called the Lagrange conditions. So the derivative of the Lagrangian with respect to x, with respect to all the lambdas have to be 0. So what would that? Okay, so the first with respect to x, so derivative of this with respect to x. So the gradient with respect to x of this function evaluated at the minimum. So if that is a minimum, this is the minimum. Okay, then this will be the derivative of this with respect to x. Here, the respect to x is because f only depends on x. So we are not explicitly saying that. So the gradient of f evaluated at that point minus with respect to x, this is a constant. So it's the sum of all these constants, and then the derivative of h with respect to h and to x. But the derivative h only depends on x. So again, we don't have to specify. And it is the gradient of h about the different lines. And that has to be zero. And then we have to compute the derivative with respect to all the lambdas. So for every lambda, what we have is the derivative of this thing is the only the corresponding constraint. So all the constraints there at that point is zero. So now here we have an equation system the same as we have here. So we have an equation system that we have to solve. We have to solve all the lambdas and we have to solve for x. Good. Okay, good. So let's look at this equation. So what is the meaning of this equation? So this equation, this is a vector. This is a vector. These are various vectors. So what we are saying, right? What we are saying is that gradient of k evaluated at the given point at the minimum is equal, it was equal to zero. So sum for all j's of lambda j times the gradient of h. This is the equation that we have right here. So this is the same here. Okay, good. Let's look at that. So let's look at something else. So let's say that vector b, this vector b is the sum for all j's or some values times some vectors. Does it remind you of something? Does it say it says that V belongs to the space span by A1. Okay. So this expand space, do you know what it is? Yeah. El espacio generado. So this is V pertenece al espacio generado por A1 hasta B. Son los vectores. Yo doy una base. I'll give you a basis. So I give you, for instance, this vector, A1, A2. I ask you, what is the space spanned by these two vectors? So it is any vector such that V can be expressed as some coefficient under one A1 as lambda 2. This is the space spanned by Okay, so any vector that can be expressed as a linear combination of these two belongs to that space. This one? Yes. Yeah, I simply put it because this equation reminds us this one. So have a vector and then a linear combination of these vectors. So what that means actually is this thing. Is that this vector belongs to space spanned by H1. So the gradient of the function must be in the space spanned by the gradient of the constraints. Always evaluate it at that point. Okay, so let's see if that's so this is a geometrical minimum. So we have a function. Here we have the isolines, isocurves of that function. So the minimum of the maximum is there. Actually, you know that the gradient goes in the direction of surface growth. So this is the maximum. Okay, so the gradient is pointing there. So this is a maximum. But you have a mountain here. You have some constraint, this one. And then what we are saying is the minimum of that problem, or the optimum of that problem, has to be in a point such that the gradient of the function at that point, this is the gradient, is in the space spanned by the gradient of the constraint. So the gradient is something that is always perpendicular. So this is the gradient field is perpendicular. The gradient field is perpendicular to the constraint. And this vector is in the space spanned by this one. So actually this one is one half of this. So this is the optimal point, this function. The maximum is here, but the maximum subject to this constraint is there. Good. Okay, so now let's make it even more general. So Lagrangian conditions, they were only valid for equality constraints. What if we have inequality constraints also? Then this is the most general setup in which we have a function to minimize, and then some inequality constraints and some equality constraints. And we will not see the derivation of that. But now we will have some conditions similar to the Lagrangian. So what we have is now this equation. So this is called the stationarity condition. So we have up to, except for this part, it's the same. So the gradient of function has to be in the space spanned by the gradient of the equality constraints. And what kind of looked conditions are is that no, it is not only this space, but the space spanned by this, and this is coming from the inequality constraints. So we have extended the Lagrangian, but then there are more conditions. So the conditions are as in the Lagrangian conditions, or the Lagrangian conditions. The second set conditions, they were coming from the constraints. Okay, so now it's the same. So as to fulfill the constraints, the equality constraints, but also the inequality constraints. So you can imagine these are coming from the derivative of the function, the Lagrangian function with respect to lambda with respect to and these are called the primal feasibility conditions. There are some other feasibility conditions that are all the lambdas have these guardians. This was not the case. The Lagrangian conditions of the Lagrangian conditions lambda take any value, but here they have to be diagonally considered. And there are another set of conditions that are these complementary slackness. That is lambda times g for all the inequality constraints. have to be zero. Now we have an equation system again. So all these are given us an equation system, very large equation system that we have to solve. Very good. Then, does it mean, for instance, here? So let's give another example. So this kind of similar example where now this is the minimum. This is the minimum. So the gradient, and we want to minimize this function with respect to feasibility to inequality conditions. One of them is this one, so it has to be larger than that. The other one has to be larger than that. Okay, so on the Canister conditions tell us is that the gradient of the function has to be in the space spanned by the gradient of the constraint. Okay, so let's look for the gradient of the constraints. This constraint, the gradient is this one, is the perpendicular line to it. This constraint, the gradient is this one, the line perpendicular to it. And what we are saying is that the gradient of your function has to be in the space spanned by this two. Okay, so good now. Okay, then let's give an example for this. So some numerical examples, but it doesn't stay here in the air. So let's say that we want to minimize this function subject to this constraint. So first of all, we realize that this is a convex problem. In a convex problem, these conditions are not only necessary, but are also sufficient for global. So we know in a complex problem, every local minimum is also a global minimum. So the first condition is these conditions, if the problem is not complex, so all minima have to fulfill this, all the points that fulfill this, not necessarily are minimum. But if the problem is complex, then that is a minimum point. Okay, then, so the function is complex and the constraint is linear, which is also a feasible region that is complex. Okay, good. So then first we have to divide the constraint in this form. So something smaller than zero. So take all this part, the right hand side, and then we have 1 minus x1 minus x2 is smaller than zero. Now we have written already the constraint, the form g is smaller than zero. Then you define the Lagrangian. When you define the Lagrangian, that is the function plus or minus, it doesn't matter. So have the function plus lambda g. Then we put all the conditions. So all the conditions are stationary. Stationarity is the derivative of the Lagrangian with respect to 1 and x2 up to 0. So this is this one is straight. So it's the derivative of the Lagrangian vectors. Because we have two x's, we have x1 and x2, then derivative with respect to those. So these are the two constraints. Okay, and this is the very simple equation, x1 equal lambda half. That's the same for this one. So we have x1 and x2 is lambda half. Then we have the primal feasibility, that is simply the constraint. Then we have the dual feasibility, that is lambda, that is 0. And then we have the complementary slackness, that was lambda times t. Okay, Okay, and then we have to solve this equation system that doesn't seem to be difficult. Okay, so from the stationarity, we have x1 and x2 are equal to lambda half. So that means that if I add the two, so they have this lambda. Okay, so then I substitute into this straight here. So here, what I have is x1 plus x2, because I have 1 minus parentheses x1 plus x2. So x1 and x2 plus x2 is lambda. So then here what I have is 1 lambda times 1 minus lambda. Okay. And also in the constraint, so in the constraint, we also have x1 plus x2. There is 1 minus lambda is greater than 0. That means lambda is larger than 1. And then from the complementary slackness that we have lambda times 1 minus lambda has to be 0. So if this is 0, it is because this is 0 or because this is 0. Lambda equals 0 is not feasible. So lambda has to be larger or equal 1. 1 minus lambda equals 0, that means lambda equals 1 is feasible with this one. So lambda is 1. If lambda is 1, now x1 and x2 is 1 half. So then we have the optimal point, that is 1 half, 1 half. The minimum value there is 1 half. Again, so you have to substitute the function 1. And then we may check what happens with the constraint. So the constraint both x1 plus x2, x1 and x2 plus x2 larger or equal 1. In this case, we have x1 and x2 is 1 half, so we have equal 1. So it is larger or equal 1, so it is equal 1. So we say that the constraint is tightly met. So we are just in the boundary of the constraint, which is typically the case. We have started with unconstrained problems. These unconstrained problems means no constraint. And then we simply look for the derivative equals 0. But when you have constraints, typically the optimal points are in the boundary of the constraint. If it is an quality constraint, they have to be on the constraint. I think it is the quality constraint, very typically the optimal are in the boundaries because the function is growing or decreasing in one particular direction. And then because of the boundary, because of the constraints, you cannot go to the minimum. Then you stay the farther you can go allowed by the constraints. Okay. Okay, so then let's move on to something else that is also very interesting. That is how to deal. We have said derivative equals 0. So derivative, when you have a one-dimensional function, a scalar function, then you all know this derivative of differentiation function. So the derivative of a constant is 0. The derivative of x to the n is n x to n minus 1. The chain rule, so you know all this differentiation. Okay, the same exists for vector value functions, not vector value, or vector argument functions. So the result is a scalar, but the argument is a vector. And the same exists also if the result is a vector. But the ones we are interested now, the result is a scalar. So if you have a multivariate function, the result is a scalar. Multivariate means the argument is a vector. Okay, then there are also a lot of rules for differentiation with that complex. So for instance, let's say that we have a constant vector. So a constant vector differentiating with respect to x. The constant doesn't depend on x. It's a zero, but now it is not zero, it's a zero vector. The derivative of x with respect to x in a scalar it is 1. For vectors it is identity with fixed. And the derivative of ax with respect to x, it is a or a transpose. So this depends on how you arrange your vectors, your differentiation vectors, whether it is a column or it is a if it is a column, so how you organize your grid. If you put it as a column vector, as a row vector, or whether you here you see is x1 squared, x1 x2, x1 xn, or you transpose it. So depending on how you organize the writing, it is a or a transpose. It has the kind of the same flavor as the scalar derivative. So for the scalar derivative, this is ax, the derivative is a, and this is you don't have the equivalent in the scalar, which is x transpose a, so it's a transpose. But depending on which is your function, have also some differentiation rules for multivariate function. Okay, now let's use that table. The full table I have just copied the beginning of it, but the full table is. So let's use that for solving a very well-known problem. So we presented this problem yesterday, least squares. So the least squares is I have some linear regression of y points on x, and then I have to find, so x are my x is, I have x, y points, and I have to find the matrix A that transposes x and y. Okay, so let's look for that for the basic things. So first thing is I'm minimizing with respect to x. So I'm minimizing with respect to x. This. Let's put it in a regression setup. Regression setup. Let's say that we are dealing with x, y values. So actions of x are these are not vectors of size, just the scalar that we find. Okay, and then I say y is beta 0 plus beta 1 x. So I can write this in a matrix form. So I can say y1, y2, yn is equal to. So this is equal to 1, x1, 1, x2, 1, xn. I agree with that. So I have to find these, the beta 0 with the 1s, and these are my predictions. So what I have to find is minimum of vector. This is a matrix. This is beta vector. I have to find vector beta. Yeah. So this has the same structure as this one. have the same structure. This is y minus some matrix times vector, and I'm minimizing with respect to the vector. But this x here is general setup. It is not the same x in here. So it is not the same x. This x goes into the matrix. And your x is your unknown. You are minimizing the respect to that. In this regression model, that now is theta. In general, we will call it x. Okay. Okay, good. So then I have the square norm. But the square norm, this is a vector. This is my residual vector. These are my observations. These are my predictions. So this is the difference between my predictions are the truth and the observed vectors. And so this is my prediction error. Minimizing the prediction error is minimizing the prediction error. Okay, good. So then this is norm of a vector, but the norm of a vector is that vector transpose times the vector. Is that right? Okay, good. Then we can expand that. That is something that may not be mine. So if you have so we have right. So it's low, so this is y transpose minus x transpose and I transpose y transpose, but all these are vectors. The transpose of the multiplication is x transpose. You have a multiplication, you want to transpose it, have to transpose it to the order of. Okay, so that is what I'm using here. So you expand this thing. Now you have some parentheses times some other parentheses. So you do first with first, first with second, second with first, second with second. Now this is what we have here. You end up with this. So this is the norm. So this is the norm of the size of your prediction errors. So this is what we want to minimize. And now I'm minimizing this with respect to x. With respect to x, this depends on x, this depends on x, but this does not depend on x. So we don't need to take care of that. And then we compute the gradient. So it is the gradient of the first one. So if you look at the derivative and tables that I mentioned before, for the derivative of x transpose some matrix, then x is twice that matrix x. And then the derivative of this thing, that is minus 2x minus 2, it works as in the standard derivative. So a constant comes out the derivative. So the derivative of x transpose and then a vector, it is that vector. Okay, so now the gradient of A is this thing plus this thing. Then that has to be 0. So that has to be 0. The two cancels, then what we have here is this equation. And this is called the normal equations of the problem that you were trying to solve. We're trying to solve this problem. These are called the normal equations of that problem. So now I have to solve for x. So to solve for x, I can take this matrix and invert it, multiply by the inverse of that matrix. This cancels here, then it goes to the other side. It's A transpose A minus 1 and A plus 1. And so X is something multiplied by Y. That something will be called the Moore-Penrose pseudo-inverse. That thing, it is denoted as A plus. So A plus is defined this way. And it can be shown that it is also equal to this one, depending on whether, so A in general will be a non-square matrix. A M N. So that means that we have n equations, n unknowns. So depending on whether you have more equations or unknowns or the opposite, or m is larger than n or n is larger than n, then we define a so here the statement is if A is not full rank, so it's not the rank is not M or N, or it is not tall, and the definition of a tall matrix is this one. A is tall, it have more equations than unknowns. Then the pseudo inverse generalizes this. But we have, so this is if you don't have more equations than unknown. But in the general case, you should have more equations. Then this is the standard calculation of the So this solution is extremely well known. This pseudo inverse solution, and we have fully derived following the same tricks that we use to minimize the state of the pattern. And what did we do with the pattern? So we had a function, computed the derivative of that function with respect to the angle equal to 0. And result for the minimum. So here it is the same, exactly the same. Only that now the function is a multivariate function. Something more complicated, the derivatives are not the standard derivatives are used. But we follow exactly the same path, exactly the same. With the derivative, and now the derivative equal to 0, the derivative equal to 0. So base of the thing. Okay, so let's make break. 21. This extend the problem even more. So we have the least squares problem. Another very well-known problem is this rich regression. So rich regression is the standard least square plus a regularization on the x parameters. So on the beta 0, beta 1 parameters that we have in the regression. So these regularization here. Now I am you can try to follow the same procedure as we did before. Here, the gradient equated to 0 and so on. And the result will be this. So the result at the end is almost the same that we had before, except for something that is this lambda has gone into the inverse, and somehow this x transpose x transpose the derivative of that translates into an identity matrix. So now you recognize what is the role of this. So the role of this is this inverse can be unstable. So when you invert the matrix, let's say that your matrix has an eigenvalue that you have to transpose revert A transpose A. So let's say that A transpose A, some of the eigenvalues are zero, and then you cannot convert it, or very close to zero. If it is very close to zero, then the inverse is very unstable, and you would be amplifying the noise there. So you want to make this inverse that is stable. And now you recognize what is the role of this thing. But the role of this thing, if lambda is big enough, then the eigenvalues of the whole thing are dominated by lambda. And then you can always make this as stable as and this matrix is always positive definite, so you don't have, for sure, you don't have zero eigenvalues. And the inverse exists even if A transpose A is that, so even if this has zero eigenvalues, A transpose A plus lambda I does not have zero eigenvalues. So you can always infer that. And so this is another famous regression problem. Of this famous regression problem, recognize it is almost the same solution as the least squares problem. So as the pseudo inverse, except that the matrix that you are inverting, you are modifying it with respect to this penalization. And this is an equation system. So we saw it before, that here's again. So here, the normal equation is a linear equation system. So this equation system can solve it at once, as we have done by inverting, or you can use other numerical algorithms to solve equations instead. So for instance, you can use Cholesky decomposition, QR-based methods. These two typically they are much better behaved than this inversion. So inversion, if you have problems with eigenvalues, the inversion is very unstable. But this Cholesky decomposition of QR-based methods, they are quite stable. They are not so sensible to small eigenvalues. Okay, so again, this was a minimization problem. Wanted to minimize something unconstrained. Actually, these are constrained, this rich regression problem. This term is also something very well known that is called the Tikhonov regularization. So it is the standard problem plus something that penalizes solutions in which x is large in terms of non. And so you can solve the equation systems at once, or the optimization problems and solve it at once. So for grid regression and for least squares, there is an analytical solution. Or you can solve the optimization iteratively. So that prompts us to a different kind of family of options. So instead of what we have done before is, okay, we have some goal function to minimize, and I will tell you at once only some complicated calculations, but you don't have to iterate. I will tell you where the minimum is. Now we will do something different. Now you will start something, and then you will move through this function trying to find the minimum. And those families of algorithms that called iterative algorithms. And the idea is that you create a sequence of approximations, of estimates of what the minimum is. And in the limit, if you iterate forever, you get to the minimum. This minimum may be local, but typically it is local. And sometimes, depending, for instance, if the problem is complex, you know that any local minimizer is also a global minimizer. In general, you are not guaranteed to get a global minimizer. We will see across the course there are some algorithms that in the infinity, they guarantee reaching the global minimum, even if the problem is is non-polynomial. We will see that in time. In general, this approach is compared to a local minimum. So the idea is that you have some kind of an estimate of where what the minimum is, and then you will update that estimate to the next one by searching in some direction, or by moving some direction, some amount. Okay, so this is the current estimate plus something that I asked. So let's make it for this is my current estimate, X. And then there is a direction, E, K. K is the current state. And then I move along that direction. I move something indicated by alpha K. The iterations typically they are put in parentheses as an upper street parentheses. And then my next one, X K plus 1 will be XK plus alpha K times K. So at every point, I decide which direction to go, if A. And then I decide how much I should go in that direction. Typically, I have drawn it like this to make it clear. Typically, alpha base is smaller than 1. So actually, much smaller than 1. So you move just a little bit in this direction. That is a typical thing. Okay, so alpha K, this thing is called the learning rate. If we have done something with or step, learning step. So if you have done something with neural networks, the learning rate is exactly that. Okay, good. So that is what we have here. So we have a current point, and then we move some amount in the direction A. So which directions are interesting? So one obvious direction is the gradient. So the gradient goes in the direction of maximum speed. So this the maximum slope. So it is growing in that direction. So I'm trying to minimize the function. So instead of going in the direction maximum slope, I go in the opposite direction. The opposite direction minus the gradient. So it's a gradient descent. Rather than going in the opposite direction, so this is almost the same. But now we have introduced a new matrix. Now we recognize this matrix. This matrix is the inverse of the Hessian. So the inverse of the Hessian has to do with something, how you approximate the function, the neighborhood, in your neighborhood. So let's say that we have some function, y, x, some function like this, and I want to minimize it, maybe the rows, but I'm here. Okay, so I'm there, and then I can make several approximations. One is that I can approximate it by a line. 1 degree polynomial. 1 degree polynomial. Or I can approximate it by, say, a parabola. Then it would be second degree. So if I'm approximating by a line, then you move in this direction. But you don't know how much you have to move, so you don't go too far. But if you have a second degree polynomial, okay, it's true that it is an approximation, it's a local approximation. But this second degree polynomial has a minimum. Why would I move to the minimum of that second degree? So that is somehow the idea behind this second order derivative. It is approximating the function by, if it is a multivariate function, it's this one, the second derivative is the Hessian. So somehow the Hessian. And there are many other ways of looking for interesting directions. Kind of things, quasi-neutral, conjugate gradient. Conjugate gradient actually is very, very much used. Stochastic gradient, so there are many variants. But you get the idea. I'm approximating the function locally by some plane. The gradient descent is by some plane, by some polynomial or some parabola somehow, and then trying to minimize to use that information to go into the direction that the function is increasing. Actually, you have another representation. So this is our goal function, and then we have here. It is this picture has been taken from neural network, so here somehow it is encoding the weights. So you have many weights, like just for the drawing, just as if we have only one weight. And then you approximate this by an hyperplane, that's the gradient, and then you go into the direction of the gradient. The gradient goes up, and then you go to the opposite direction. You move a little bit, which is the mental straight. Then you move to here. Then here you estimate the gradient again, and then you move a little bit, and then here you estimate the gradient again, until you get to the minimum. What if my learning rate, my step function, my step is too large or too small? So if it is too small, then you will move very slowly. You will have to complete many gradients. And maybe you reach this point after 1,000 iterations. And what if I make it too large? So if I make it too large, I approximate this by a line, and then I move a lot along that line. And what happens is that line was a good local approximation, because I don't get away from that point. It's not a good approximation anymore. So now I think that I have to move here, but then here I have this one. Start jumping from one side to the other, you might actually divert. So instead of converting to a minimum, start jumping all the time, you don't get anywhere. So that is a danger of this language. Actually, for neural networks, it is one of the most difficult things. What is the right learning rate? Because you don't know, you don't see the grade in there, but what you see is how it behaves. So if you choose a given value, maybe you see that it's converting, but very slowly. And if you increase the value, even if it seems small, you see that it starts diverging. Choosing the right learning rate is something very different. And then even you can put the learning rate to be adaptive. So where you see that there is a bigger slope, and you can take larger steps. Then when you start to see that the slope is small, you can make smaller steps. So you can change the learning rate across iterations. Actually, that was implicitly noted here, when you said every k step has its own step. Alpha k potential 3, there is no fields. Yeah, this is somehow also illustrate that depending. So all these gradient descent algorithms, they converge global minimum. So if you start here, we converge this minimum. This is the global minimum of one that you're fine. But if you start here, you'll end up at a local minimum. Here the gradient is 0, so you don't move anymore. If you move in the direction of the gradient, but if the gradient is 0, then you're not moving. And the same happens For instance, in these two-dimensional functions, you start from very close by points, but then because the gradients are different, slightly different, this one is pointing in this direction, this one is pointing in this direction. Then you get to very different local minimum. So even if you start close, here we understand we start far from each other. So the local minima that we find will be different. But these two, they start very close, they still diverge. So these things happen. Any question up here? Okay, so finish this introductory lecture. Let's remind some general facts that I know about station. Some of them have already appeared, some others have. So this one we have already said. So if I want to maximize a function, the argument that maximizes the function is the same as the argument that minimizes minus the function. So all maximization problems actually they are minimization problems. Got a question? No. Okay. These are your three. Another one is if I apply a monotonic transformation to my function, so phi is a strictly increasing function. I want to minimize f. It's the same minimizing f or minimizing f through that function. And this is very important in some cases. So, for instance, here, let's say I want to minimize. I don't want to get all the derivation, how we get to that. But say that I want to minimize exponential or some y minus x. And let's keep it like without any division. So like this. I want to minimize that. And this is related to the multivariate Gaussian right? So I want to minimize that with respect to the x. This is the vector, this is the vector, this is the vector. Okay, with the exponential, maximize that. Maximize. And this is related to maximum likelihood. Have you heard of maximum likelihood? Yes. Maximum likelihood. Sorry? Maximum velocity. Okay. If we are here, some other, otherwise I will explain. Yeah, maximum likelihood. I will explain it, but at some point, maximum likelihood, something like this appears. You want to maximize that with respect to x. Okay, but with the exponential is a non-linear. Seems that it's something complicated. So this is maximizing x and trying to maximize that. Okay, maximizing that. What if I do maximization logarithm of f of x? So the logarithm is a function like this. This is f of x. This is the logarithm of f of x. Logarithm is something. So it is a function that is continuously increasing. So if at some point x is maximum, or f of x is maximum, the logarithm will also be maximum. The logarithm f of x will also be maximum. Right? So if there is a function that is a property, this is monotonically fixed. So that means it always increases. if this function always increases, then maximizing the function or maximizing the logarithm of the function doesn't matter. But the logarithm of the function is much easier because the logarithm of the function, the logarithm of the exponential is the logarithm of the function is much easier. And the argument, you have to, this is incorrect. The maximum of this is not making it. But the argument is, the argument that maximizes the x that maximizes that. Very often we are loose and we omit the argument, but if you want to be straight, you have to put the argument. It's the same as the argument that minimizes the state. It's the same argument. So if x minimum maximizes things, x is minimizing that because of the minus. And if I'm maximizing something, 1/2 or not, I don't care. So the argument is the same. And this is the least squares problem that we already know how to solve. After the solution of that is a transpose so we have to turn a very complicated problem to something that is extremely easy to solve. I'll come back to maximum likelihood. Okay, so, and that happens for all strictly increasing functions, so all monotonic transformations. Okay, then if I add a constant, the argument that minimizes this is the same. So the argument that minimizes this and the argument that minimizes this is the same because I'm adding a constant is here simply making the mountain these landscapes that we have happen over. Then minimizing the norm, minimizing the square of the norm doesn't matter because a square is a strictly increasing function. So I don't care minimizing something or the square of that. And that is important. The square is strictly increasing in the positive side, but this is positive because this is non. On the other side, the square is x squared. Shape of the function. Here it is decreasing. Here it is increasing. Only on this part. The other part is decreasing. But if my x is here, then it is a monotonic increasing function. Then I can apply it's a monotonic increasing function. So completing the square with maximizing the square. No, we don't care. But only this range. Then let's compare the minimum over the with some constraints or without constraints. So let's say that we have the unconstrained problem. For the unconstrained problem, we find the minimum. but the minimum is not in the feasible set. So when you look at your constraints, the minimum of the function is not within your set, your constraints. So the constraint minimizer lies in the boundary. This has appeared already multiple times. So, we have it with the values in prepared conditions. So the minimum was here, but because we are restricted to this area, we try to approach, we are going down the hill, trying to get to the valley, but at some point we are stopped by a fence. Then we have to stop them. Okay, so if the minimum, the global minimum, here, the global minimum is outside our feasible scale, we have to stay at the boundary of the feasible scale. Then, if the function is convex and x, the minimum x star satisfies that the gradient is zero, then it is a global minimum. But we don't have to check for second order conditions or whatever, because f is convex. This is zero, then it has to be for sure global minimum. And the last property is this one. So let's say that we express Z as AX plus B. This is called an affine transformation. X times A times X plus B. It's an affine transformation of X. X is a vector, this is a matrix, this is a vector. And then minimize function over Z is the same as minimizing f of ax plus b over x. So it is somehow doing this kind of things. We had so here we did it with increasing monotonically increasing functions, which is transforming the problem to something that is easy. So we transform this difficult problem into something that was pretty easy. And then this is the same idea. Right? It's not the same transformation, but it's the same idea. Sometimes you have a difficult problem, you transform it into something else. Then this something else might be easier to solve. And here you see this function. So the only thing that's changing is a constant vector. So sometimes we can remove constant vectors. So this maximizing with respect to something that does not depend on this constant. Sometimes you move from right. Any question? Maximum likelihood. Okay, so the maximum likelihood is this. So maximum likelihood means I'm doing it in dimensions because this is by that last way. So I have some points. And I want to find these functions. I estimate is equal plus without 1, x plus without 2, x squared. And I want to find the betas that maximize the likelihood of observing these y's. So check the time. So then I have to put them on. So my model is that y is some function of x plus some noise. This noise follows a random distribution. The most difficult one is it is not the only one. I assume so. This is for every point. Okay, so these are statements. They are not vectors. So my assumption is there is some underlying function that I'm trying to estimate. It's vector 1. but my observations are disturbed by some noise. You have seen this setup in some courses, right? I guess. Okay, so then uh, I'm given the collection of X, Y, Y, observations. So I will try to look for the I will try to look for the data signal, data parameters such that because F is expressed at second. So I will try to find the beta parameters such that the likelihood of the likelihood of observing Y sex is maximized. And this likelihood is coming from this distribution. So this is maximum. So what is Y given X? Y given X state. So this is the same as if I'm trying to maximize that like this likelihood, something like this. So it is maximum when the error is small. So I'm trying to look for what are the betas that make this epsilon be as close to zero as possible. And then if you plug in the formula of the normal, the end, which remember the formula of the normal, right? So it's a maximum. We're writing for it. Okay, everything is maximum. Observations, multiply overall observations, then I would write it to the one. So then, explanation. And somehow can imagine that this multiplication, constrains this norm somehow. That is maximum likelihood. So you are trying to maximize the likelihood of observing these Y's, even these X, with when what I can tune are the betas. Maximum likelihood. Why these are very much used framework for estimating parameters in noise settings. Any other question?